Jupiter is not what you think it is, not even close. For decades we were taught a simplified version of this massive world, a version that fit neatly into textbooks and made the solar system easier to understand. But Jupiter refuses to be simple. Jupiter refuses to be predictable. And the deeper we look into this enormous planet, the more it becomes clear that almost everything we believed about it was wrong. Scientists once described Jupiter as a gas giant, a huge sphere of hydrogen and helium sitting peacefully in the outer solar system. That definition is comfortable, clean, straightforward, but it's also misleading, because beneath Jupiter's swirling atmosphere lies something so strange, so extreme, so violently foreign to anything we know, that no classroom explanation ever truly captured its reality. The truth is that Jupiter is a world built on extremes, extremes of pressure, extremes of temperature, extremes of physics. It is a planet made not of familiar rock or gas, but of states of matter that we barely understand here on Earth. And as modern spacecraft have begun peeling back its layers, Jupiter has revealed itself not as a simple gas ball, but as a layered, churning, shape-shifting entity full of deep mysteries and impossible structures. Our journey to understand Jupiter begins with the earliest close-up photographs. When Pioneer 11 sent back its first images in 1974, humanity saw Jupiter's surface with clarity for the first time, a swirling world of bands, storms, and chaotic colors. 5 years later, Voyager 1 delivered the first moving image, a hypnotic time-lapse of storms spinning, colliding, and evolving in ways that felt alive. Beautiful, yes, but also deceptive, because as stunning as these images were, they revealed almost nothing about what was happening beneath the planet's cloud tops. And so the biggest questions remained unanswered. What is Jupiter truly made of? How deep do its storms go? Does it have a solid surface? Does it have a core? And if so, what kind of core could survive inside a world of such unimaginable pressure? Before we can go deeper, we need to grasp the scale of Jupiter, because understanding Jupiter's size is essential to understanding its behavior. Jupiter is enormous, not big planet enormous, not several times bigger than Earth enormous, but incomprehensibly, absurdly, impossibly enormous. You could fit more than 1,000 Earths inside it. It is heavier than every other planet combined. If Earth were the size of a grape, Jupiter would be a basketball. But this incredible scale hides something far more important. Jupiter's mass creates a gravitational pressure so extreme that it reshapes matter itself. It crushes atoms, bends electrons, and transforms hydrogen, the most common element in the universe, into forms that do not exist naturally anywhere else. Whatever Jupiter is, it is not merely a gas giant. It is a planet-sized pressure chamber. The early theories of Jupiter's formation were simple. Jupiter formed from rock and metal, just like the other planets, but grew so massive that its gravity began to capture the lighter gases of the early solar system. These gases collected around a rocky core and eventually formed the Jupiter we know today. Under this theory, the planet should have a massive, dense, well-defined core, the remains of the early rock and metal that seeded its growth. This explanation made sense, but it was incomplete, because later observations revealed that Jupiter's interior does not behave like a world built around a solid core. Instead, the deeper we looked, the stranger Jupiter became. And then, by sheer cosmic coincidence, the truth began to reveal itself. In 1994, comet Shoemaker-Levy 9 slammed into Jupiter in one of the most spectacular cosmic events ever witnessed, a once-in-6,000-year collision. The comet struck the planet with the force of hundreds of millions of atomic bombs, sending debris exploding thousands of kilometers above the cloud tops. And as those plumes rose, they carried something with them, material from Jupiter's hidden interior. For the first time, humanity got a glimpse of what Jupiter was made of beneath the clouds. And alongside exotic chemicals and strange compounds, there was water. Far more water than anyone predicted. Enough water to challenge everything scientists thought they understood about Jupiter's formation. The discovery raised questions that could not be ignored. Why was there so much water in a world supposedly dominated by hydrogen and helium? Where did it come from? What did it reveal about Jupiter's origins? NASA needed answers. and so a new mission was born. Launched in 2011, Juno was designed not to observe Jupiter's surface, but to penetrate its secrets, to map its magnetic field, to measure its gravitational anomalies, to peel back its layers like an X-ray. When Juno arrived in 2016, scientists expected surprises, but not the kind of discoveries that would rewrite the entire structure of planetary science. One of the first revelations was the behavior of Jupiter's storms. The Great Red Spot, a storm large enough to swallow Earth, was thought to be a shallow atmospheric phenomenon. But Juno discovered that it extends deep into the planet, hundreds of kilometers down, in ways that implied a connection to something far more powerful beneath. More shocks followed. Jupiter's atmospheric bands weren't just flowing horizontally, they extended downward thousands of kilometers into the planet's interior. These jet streams behaved less like individual weather patterns and more like the visible skin of a deeper planet-wide engine. But none of these discoveries compared to the revelation that came from mapping Jupiter's gravitational field. As Juno orbited Jupiter, it measured tiny changes in speed caused by subtle variations in Jupiter's internal mass distribution. These shifts were so delicate that only a craft as precise as Juno could detect them. And what these gravitational signatures revealed was astonishing. Jupiter did not have a traditional core, it did not have a solid central sphere, it did not match any planetary model ever built. Instead, deep within Jupiter lay something that seemed impossible, a core that was massive but not solid, dense but not compact, mixed but not uniform. Scientists began calling it a fuzzy core, but even this phrase fails to capture what Juno truly found. The core was not a single object but a gradient, a swirling blend of rock, metal, ice, and metallic hydrogen, all stirred together in a vast, chaotic, semi-liquid mass. It spread across nearly half the radius of the entire planet. It refused to settle into a stable shape. It behaved more like a planetary storm than a solid body, and its existence raised a terrifying possibility. Jupiter may have collided with a planet 10 times the size of Earth. But even this catastrophic explanation failed to fully account for what Juno found. Juno's discovery of the fuzzy core shook planetary science to its foundation. Until then, scientists believed they understood how planets formed. They believed they understood how gravity arranged matter. They believed they understood how the architecture of the solar system came to be. But Jupiter, the largest world orbiting our sun, defied all expectations. Instead of revealing a neat, layered interior, Jupiter exposed a tangled, chaotic blend of materials, a planetary heart that refused to behave like a heart at all. To understand just how bizarre this is, imagine dropping a stone into a lake. The stone sinks. Heavier materials always move downward. Lighter materials rise to the surface. This is how planets form. This is how stars form. This is how the universe organizes itself. But Jupiter's interior seems to ignore these rules. Instead of a compact, dense object in the center, Juno detected an extended region of heavy elements mixed into a vast, fluid environment, as if something once shattered Jupiter from within and prevented its core from ever settling again. If Jupiter did collide with a massive rocky planet, the event would have been one of the most violent in the history of our solar system. Picture it. A planet the size of 10 Earths slamming into proto-Jupiter at tens of thousands of kilometers per hour. The impact would have sent shockwaves rippling through Jupiter's interior, vaporizing rock, liquefying metal, and scattering heavy elements across enormous depths. The collision could have disrupted the newly forming core so severely that it never reformed into a solid shape, leaving behind the strange diluted core observed today. But here's the problem. When scientists simulated such a collision on supercomputers, they found that the core should re-solidify within a few million years. Jupiter is billions of years old. So why is its core still fuzzy? The answer might lie in a far stranger phenomenon, one that astronomers rarely discuss openly. It is the possibility that Jupiter's interior is not governed solely by typical planetary physics. Something inside Jupiter may be redistributing heat, mass, and energy in ways that current models cannot explain. Something deep in Jupiter's metallic heart may be preventing the core from ever settling into a stable shape. And this brings us to perhaps the most visually stunning, but also scientifically puzzling discovery Juno ever made: the cyclones at Jupiter's poles. Before Juno, astronomers had never seen Jupiter's poles up close. All previous missions orbited near the equator, leaving the northern and southern extremes shrouded in mystery. But when Juno finally flew over Jupiter's poles, the images sent shockwaves through the scientific community. Instead of chaotic storms, Juno saw geometry, perfect geometry. At the North Pole, 8 massive cyclones arranged themselves in an almost mathematically perfect octagonal pattern, each storm the size of a continent, each spinning independently, yet locked into a stable formation. At the South Pole, a similar pattern emerged, this time with 5 storms in a symmetrical ring around a central vortex. These storms are not drifting, they are not merging, they are not behaving like storms anywhere else in the solar system. Instead, they are held in place by something deep beneath the clouds. Some hidden internal structure or force appears to be anchoring them in position. Fluid dynamics alone cannot explain these polar cyclones. Atmospheric models break down, simulations fail. Nothing behaves this way unless the atmosphere is being influenced by a deeper, more powerful engine. This engine is Jupiter's metallic hydrogen layer. To grasp how extreme this layer is, we must go deeper into the planet. Beneath the ammonia storms, beneath the water clouds, beneath the 1,000-kilometer ocean of liquid hydrogen. At a depth where pressures reach millions of atmospheres and temperatures climb above 10,000 degrees, hydrogen undergoes one of the strangest transitions in all of physics. It becomes metal, a liquid metal, capable of conducting electricity, capable of generating magnetic fields, capable of sustaining currents so vast they dwarf the total electrical output of human civilization. This metallic hydrogen does not sit still. It swirls, it churns. It rotates faster than the atmosphere above it, and as it moves, it generates Jupiter's extraordinary magnetic field, a field so powerful it stretches millions of kilometers into space, creating a magnetosphere larger than the Sun itself. The magnetic field is not symmetrical, it is warped, twisted, bent. It possesses anomalies, one of which is known as the Great Blue Spot, a magnetic storm deep within the planet that drifts across Jupiter's surface like a living creature. Juno tracked this anomaly as it moved, slowly, steadily, unpredictably. No planet should generate a magnetic feature that behaves like a migrating storm, yet Jupiter does. And this opens the door to an astonishing possibility. Jupiter's magnetic field may be shaped not just by its metallic hydrogen layer, but by something deeper, something in the fuzzy core itself. If heavy elements and metallic hydrogen are truly mixed together on a massive scale, they could create internal structures that act like anchors, influencing everything above them, from magnetic storms to atmospheric cyclones to the Great Red Spot. But if that is the case, then Jupiter is not simply a planet. It is a system, a complex, layered, evolving machine driven by physics that do not exist naturally on Earth. Still, the mysteries do not end there. In late 2024, new gravitational models combined with infrared scans revealed something that stunned the scientific world. Beneath Jupiter's atmosphere lies a pattern, a repeating signature buried deep within the planet. It was not random, it was not chaotic. It suggested some kind of layered structure or transition zone hidden thousands of kilometers below the clouds. Some scientists believe this pattern reveals the boundaries of different metallic hydrogen phases, sheets or slabs of material arranged like continents drifting beneath Jupiter's surface. Others think the signatures may represent internal waves of density, rising and falling like tides in a vast liquid interior. And then there is the most extreme theory, the idea that deep inside Jupiter exists a nuclear ocean, where pressures and temperatures are so extreme that hydrogen fusion may occur on microscopic scales. Not enough to ignite the planet into a star, but enough to produce strange, unfamiliar forms of energy. If this theory is correct, Jupiter may not be a failed star, but an entirely different class of object altogether. Whatever the truth is, one thing becomes clear. The deeper we go into Jupiter, the more the planet behaves like something alive. Patterns, structures, stable forms within chaos, hidden layers that respond to energy, a magnetic field that pulses and shifts, atmospheric bands that act like the visible skin of the mechanical heart beneath. As our instruments grow more precise and our missions dive deeper into Jupiter's gravity well, one truth becomes impossible to ignore. Jupiter is not just a planet. It is a laboratory of extreme matter, a relic of the solar system's violent birth, and a window into the physics that shape not only worlds but entire star systems. Every new scan, every new measurement, every new orbit of the Juno spacecraft pulls back another layer of the giant, and every layer reveals something stranger than the last. Jupiter challenges our understanding of how planets form, how they evolve, and how the laws of nature bend under unimaginable pressure. And maybe that's why Jupiter matters more today than ever before. Because when we study this massive, turbulent world, we are not just looking outward, we are looking inward, toward the origins of Earth, the fate of our solar system, and the boundaries of what is possible. Jupiter reminds us that the universe is still full of mysteries we barely comprehend, forces we do not fully understand, and worlds that refuse to fit into the limits of our imagination. And as long as it continues to surprise us, we will continue to chase its secrets, peeling back the layers one discovery at a time. Because somewhere beneath those swirling clouds lies an answer, one that may change how we see the cosmos forever.